So we will now do 8 exercises that are related to chapter 5. Let me see. Yeah, I'm going to scroll to the answers and then discuss them there. Actually, I did not post PDF. Usually I would post it in advance. The reason I didn't post it is I didn't want that to pop up while you were preparing for the exam and then distract you from that. Some of you may be curious and when you should be studying for the exam. So molecule below is an amphiprotic compound. It's actually cyclopentanol. Provide formula of its conjugate base and conjugate acid. Amphiprotic means that it could either accept or donate proton. So that means it could act either as an acid, accept a proton, donate proton, or as a base, accept a proton. And so you start with cyclopentanol, and then if you look at what is conjugate acid, it's protonated species. So when cyclopentanol accepts a proton, conjugate acid is obtained. So you need to look at this molecule and consider which atom has free electron pair and this basic atom that can be protonated. And only oxygen has free electron pair. Actually, it has 2 free electron pairs. Only oxygen can be protonated. And so this is conjugate acid. To find conjugate base, again, you look at the starting compound, cyclopentanol, and consider which of the protons is acidic. And remaining 11, or actually not 11, it's 9 protons, 9, 2, 4, 6, 8, 9 protons. The remaining 9 protons are carbon-hydrogen bonds. Those are not acidic. Only OH bond is acidic. That's the proton that can be removed. So removal of that proton gives conjugate base. And so those are conjugate acids and conjugate bases. In this case, you may be asked to type up conjugate acid or conjugate base. But if you were to do that, actually, let me just add one more question. Yeah. Okay. Let's say methanol is an amphiprotic compound. Provide formulas of its conjugate acid and conjugate base. So you consider methanol. And you would need to type it up. So methanol, you would type it up as CH3OH. That's methanol. And the conjugate acid would be protonated. So oxygen is protonated, the same way this OH2 is protonated. So you would 2 and plus. And that's it. So this would be acceptable answer for the test. Now, what you really should do, if you are typing it up, let's say in a paper or something like that, you would put 3 in a subscript, 2 in a subscript, and plus superscript. But on the test, because these symbols may be time consuming for you, I'm not going to require that. So you simply type it up like this, and that will get you all the full points. Conjugate base would be the protonated species. So that would be oxygen minus. And so you need just a minus sign. I'll put it like this. Okay, this was supposed to be this one. Okay. No, it's not showing up. I made a mistake. I used underline instead of. Okay, so this is minus. You can see it. It's a small one, but you can see it. That's the minus. Okay, so whatever. Oh, okay, I can see one problem. Yeah, this is now much cleaner. So these on the left would be good enough for the test. If there are rings involved, then it would be multiple choice, A, B, C, D, and then you would pick correct ones. In this case, then you may have to pick out conjugate acid, conjugate base pair. Next question, arrange the following compounds in the order of increasing acidity, from the least acidic to the most. And so what we have in this case is are various nitrogen compounds, where nitrogen bonded to hydrogen is in different states of hybridization. Here it's sp2, sp3, and sp. And you may recall that hybridization is related to electronegativity. sp hybridized atom is the most electronegative, sp2 in between, sp3 the least electronegative. So when hydrogen is bonded to a particular atom, the more electronegative atom is that hydrogen is bonded to, the more acidic the compound is, because the more stable conjugate base is. And so sp is the most acidic, and then sp3 would be the least. So if you're listing them in the order of increasing acidity, you would start with sp3. No, what's going on? Okay. Then sp2. And finally, sp is the most acidic. There. By the way, last one is isocyanic acid. Maybe I can highlight in these cases. Actually, just here the answer. Okay. Okay, so next we'll be looking at a little bit more complex inductive effect. So before I do that, let me see if there are any questions. Okay, I don't see any questions. As usual, if there are any questions, type them up or unmute yourself and ask a question. Question number 4. List the following acids in the order of increasing strength. Common exam question. And in this case, so that you don't have to redraw the formula, I'm using A, B, C, D associated with each acid. And a question like this often stumps some students simply because they see cyclopropyl ring and they're wondering what that means, how does that affect acid strength, and so on. But actually, it's simple inductive effect. Inductive effect is electron withdrawal through sigma bonds. And any electron withdrawing group will stabilize the resulting conjugate base, species that is obtained by loss of proton. And so any electron withdrawing group will increase acid strength. The more electron withdrawing it is, the stronger the acid. And how electron withdrawing, what kind of effect it has, how strong that electron withdrawing effect is, depends on 2 factors. Actually, 3. Third factor will cover under question 5. But we're now looking at 2 factors. One is electronegativity. So the more electronegative atom is, the stronger electron withdrawing effect is. So that means stronger effect on the acidity. So fluorine, being the most electronegative, will exhibit higher effect than chlorine. Chlorine higher than bromine, bromine higher than iodine, and so on. That's why you will again need a list of electronegativities for the next exam, because you need to know how electronegative these substituents are. That's one aspect. Second factor is distance. How many bonds it is removed from the structural element that it is affecting, in this case OH group. This is acidic bond. So this is electronegative atom. And so how far it is. And so you can see it's 1, 2, 3, 4 bonds. In the case B, it's 1, we're looking at this oxygen, 1, 2, 3 bonds. So B must be more acidic than A because electronegative element, electronegative substituent is closer. And now what we have here when we look at these four, we have chlorine or bromine as substituent. In case uh, of bromine, compound C, that's going to be least electronegative species. So if you're providing answer, C is going to be least electronegative because bromine, if you look at number of bonds, how far it's removed from this hydroxyl oxygen, OH oxygen, it's 1, 2, 3, 4 bonds. And it's bromine, least electronegative of the two substituents, bromine and chlorine. Then you have, actually I may have made a little bit of mistake here because I put here bromine 3 bonds away and chlorine 4 bonds. And when you now you have less electronegative is closer, more electronegative further away. So that's actually a little bit difficult to distinguish. So let me change it a little bit. That changes the answer, but at least there is no doubt. So I changed this to fluorine. It's more electronegative than chlorine, so now we don't have that doubt. So now we have bromine 4 bonds away, and here we have chlorine 4 bonds away. 1, 2, 3, 4. So next acid is A. It's stronger than C because chlorine is more electronegative than bromine, but both are 4 bonds away. And now we have two substituents 3 bonds away. See, 1, 2, 3, and this is 1, 2, 3. Fluorine is more electronegative than chlorine, so that's stronger acid than B. And so answer is B and then D. That's correct answer. You can definitely expect questions of this type, 4 or 5 on the exam. I'm going to check if there are any questions just to see. Okay, let's go back to question number 5. Question number 5. List the following acids in the order of increasing strength. So I mentioned 2 factors. One is electronegativity, second is distance. Third factor is the number, because inductive effects are additive. So the more substituents exhibit the same inductive effect, the stronger the acid. And so 2 substituents exhibit stronger effect than 1, and 3 stronger than 2. And so when we look at these, actually, okay, so what we can see here is that we have all fluorine, so no problem there. But what do we have here? We have this fluorine that is, again, we're looking at OH group. 1, 2, 3, 4, 5 bonds away. That's almost negligible effect. So that's going to be acid of least strength. And then we have these 2 fluorines that are again 1, 2, 3, 4, 5 bonds away each. But this effect is going to be a little bit stronger because there are 2 of them. Now we have only 1 fluorine here versus 2 of D, but this one is only 3 bonds away. Now 3 versus 5, basically minimum distance would be 2 bonds away. It would be right here, but because of the carboxyl group, we cannot have it 2 bonds. If this is, let's say, OH and then fluorine, definitely something like that. Or nothing here, no oxygen, just CH and CF. That's with the minimum distance. In carboxylic acid, the minimum distance is 3 bonds away. So this fluorine is as close as it can get. So that's pretty strong effect. Effect sharply decreases with distance. And so 3 versus 5 bonds, with 5 bonds, it's almost negligible. So in this case, it's very easy to say that A is stronger acid than D, even though it's 1 versus 2, because A is only 3 bonds away, while D has fluorines 5 bonds away. Sorry, not A. Yeah, that's right, that's correct, A. And then C is the strongest because it has 2 fluorines versus 1, 3 bonds away. So that's inductive effect. Generally, students find that one the most complex of all the other effects. The other effects are pretty straightforward, and next one is one like that. list the following compounds in the order of increasing strength. And here we have hydrides of phosphorus, antimony, and arsenic. And in this case, actually, acidity, because they are in the same group of periodic table, when hydrogen is bonded to atoms of the same group of periodic table, acidity increases with increased size of the atom. That's because conjugate base that is larger has negative charge that is distributed over larger region of space, larger volume of space, and it's more stable. So the strongest acid is going to be the one with the largest atom that is bonded to acidic hydrogen. In this case, that's antimony. Weakest is going to be one with smallest. In this case, that's phosphorus. So this phosphorus species is going to be, it's not working. Okay, now it's working. So that's weakest of the three acids. Intermediate strength is this arsenic compound. And the strongest hydride of antimony. So as I said, this is a simple effect of atom size. Okay, I just have to see where I am. I have to show this. Okay. Okay, before we cover last three, again, let me see. Okay, no questions, so let's go back. Question number 7. This is actually question 31 from exercises, and the answer there is wrong. I think that I may have posted correct answer, fixed that answer, in a PDF version on Canvas, but in the printed book it's wrong. So here is correct answer, and that's why I worked it here in case you're wondering. So in which form iodoacetic acid, its pKa is 3.12, exists at pH 1.5? And this is formula of iodoacetic acid. So if pKa is 3.12, then above pH of 4.12, pKa plus 1, acid will exist in deprotonated form. So you look for acidic proton, that's the one. Deprotonated, that's acid will be in deprotonated form. If pH is in the range of 212 to 412, pKa plus minus 1, should be plus minus 1. pKa plus minus 1, there's going to be a mixture of protonated and deprotonated forms. And finally, if pH is below 212, and that includes pH of 150 from the question, then acid will exist in protonated form. That means that's protonated form. On the test, actually, you would type it as iodine CH2 CO2 H, and that's it. That would get you 4 points. Or CH2 iodide CO2H. So if it's not multiple choice, if you were typing it up, that's how you would do it. Question number 8. Classify each of the following compounds as a Lewis acid or a Lewis base. So Lewis acid must have empty orbital so that it can accept free electron pair. Lewis acid is electron pair acceptor, so it must have empty orbital to accept that electron pair. Lewis base must have free electron pair. It's electron pair donor. And so electron pairs are shown here. And so this compound is Lewis base because it has 2 free electron pairs. When there is more than 1 free electron pair, only one can be donated. Second one cannot. But that's Lewis base because it has free electron pair electron pair or pairs and no empty orbitals. This one is neither. This is kind of trick question and often is included, particularly in multiple choice, because it has positive charge. Frequently, species with positive charge, like carbocations, for example, are Lewis acids, and students get to associate positive charge with something being Lewis acid. But that's not what you look for. You look for an empty orbital. In this case, there is no empty orbital, and so it's not a Lewis acid. Next one, Lewis base, again, free electron pair, and no empty orbital. This is cation, metal cation, except for alkali metals, sodium, potassium, rubidium, cesium, which have no tendency to accept free electron pair. All other metal cations are Lewis acids because they can accept free electron pair. They have empty orbitals. And this is also Lewis acid because this zinc atom, even though it doesn't have charge, forms only 2 bonds. So it's 2 bonds short of octet, or two empty orbitals short of octet. And so it's also Lewis acid. This is an example of Lewis base. This is actually an acidic compound because it can donate proton, but it's Bronsted acid. That's Bronsted definition, proton donor. Lewis acid, Lewis base is definition through electron pair. Is something electron pair donor or electron pair acceptor? And so electron pair donor is Lewis base, and electron pair acceptor, empty orbital, Lewis acid. Bronsted definition is proton donor acid, proton acceptor base. And finally, here is an example of Lewis acid. Aluminum trichloride. You see, aluminum doesn't have octet field, only 6 electrons, 3 bonds, and empty orbital. So that's Lewis acid. And question number 9, final one. Which of the following substituents will make carboxylic acid a stronger acid? So electron withdrawing substituents make acid stronger acid, and conversely, electron donating make it weaker. Electron withdrawing substituent is one that has electronegativity higher than carbon. So you would look at list of electronegativities, and maybe you would know them already from periodic properties. So if electronegativity is higher than that of carbon, then that's electron withdrawing substituent and makes acid stronger acid. If electronegativity is the same or lower than carbon, then it's actually electron donating substituent, and it makes acid weaker. So in this case, you're looking for a substituent that is electron withdrawing. Boron actually has lower electronegativity than carbon, so that makes acid weaker. This is trifluoromethyl. Fluorine has higher electronegativity than carbon, and in this case, there are 3 fluorines on 1 carbon, so we consider that as one substituent, but it's electron withdrawing, so that's correct. That is correct answer. Trifluoromethyl group will make an acid stronger acid. Cyclohexyl group, some students go for this choice simply because it's cyclohexyl. It's different from the rest. It's a ring, and it's typed up instead of formula. But no, that's just carbon-hydrogen bonds, same as D, only carbon-hydrogen bonds. Electronegativity is the same or lower than that of carbon, so those two are actually electron donating. And so all those A, C, and D, they actually reduce strength of the acid. Only B increases strength of the acid. Okay, so that completes review of chapter 5. And at this point, I'm going to stop recording and then answer any questions you may have.